Hi everyone, thank you so much for joining us today. We have with us a guest speaker, Lisa Liu. Lisa is a fourth-year PhD student at University of Washington, advised by Eugene Choi and Noah Smith. She works on NLP with a focus on decoding time algorithms and security problems for language models. She is supported by NSF Graduate Research Fellowship and OpenAI Super Alignment Fellowship. Today she will be presenting her research paper, Data Mixture Inference. What do BPE Tokenizer reveal about their training data? Thank you so much for your time, and I'll pass it over to you.
Hi, everyone. Thanks for the introduction and also for inviting me to give this talk. Feel free to interrupt me at any point if there are questions during the talk. So today I'm excited to share our work, Data Mixture Inference. What do BPE tokenizers reveal about their training data? We study how to uncover distributional information about the training data given a trained tokenizer. And I did this work together with John Hayase as co-first authors, as well as the union of our amazing advisors. So a really important question these days is, what are large language models trained on? Increasingly, we see that model improvement is not driven by advances in model architecture, but better data curation. So some important design decisions include, for instance, the proportion of different languages and data sources in the training data, as well as the amount of code. So these decisions essentially remain a trade secret for today's strongest models. They require extensive experimentation that few organizations really have the resources to perform. And in particular, it's increasingly common for model producers to open source their model parameters without actually sharing any details about pre-training, such as the data composition. So all of these models shown here are examples of that, where we have access to the model weights, but we don't really know much about the pre-training data. So that led us to formulate a task that we call data mixture inference, where the goal is, given a set of disjoint categories that cover the training data, to infer the proportion of each one. And we're going to study, for instance, we're going to infer, for instance, the distribution of natural languages and the amount of code that's in the training data, as well as the distribution of different domains. And in our work, we're going to focus on BPE tokenizers and infer their training data distribution. So tokenizers have been largely overlooked as an attack surface, but we show that they actually contain a ton of information. In particular, we're looking at byte-pair encoding tokenizers, which are like the de facto choice for essentially all language models today. What's neat about this is that tokenizers are also often open even for closed models. So for instance, GPT-4o and Claude are completely closed in the sense that we don't have access to their weights, but their tokenizers are actually open source. And that's because these companies want users to be able to estimate the cost of their queries ahead of time in terms of the number of tokens before using the API. And yeah, why do we care about tokenizer training data? So ideally, the tokenizer training data is representative of the pre-training data. The most, I guess, obvious thing to do would be to downsample the pre-training data and train your tokenizer on that. Disconnects between the tokenizer training data and the model's pre-training data will lead to poor encoding of text, as well as potentially glitch tokens, which are essentially undertrained tokens that then lead to really degenerate behavior in the language model. The tokenizer training data also gives you a sense of the priorities of the model creators. What the tokenizer is trained to encode in many ways restricts the kind of text that the language model can learn to model, right? And training a tokenizer is the first step to model development because you need to use it to encode your pre-training data. So this is telling you what the model producers want the model to be able to support now or eventually. And knowing this data can also potentially accelerate other model-based attacks. So let's say, for instance, you have a membership inference attack, but you can't run it for every possible example that might be in the training data. So if we know the tokenizer's training data, then that can give you a sense of what examples you want to prioritize for your MIA attack. Before I explain our attack, I'll give some background on how BPE tokenizers are learned. During this section, especially if you already know this information, you can maybe think about how one might construct a data mixture inference attack given how BPE works. So let's say our tokenizer's training data is this very simple 10 Tweedle Beetles battle, which is from Dr. Seuss, I guess. The first step of training is to pre-tokenize the text into words. So these essentially represent boundaries on how big our tokens can be. The final learned tokens are going to be parts of these words. Pre-tokenization can be as simple as splitting on white space. So that means that sequences of words that are common, like it is, do not become a single token. It's also popular to pre-tokenize individual digits, which is what I'm showing here, although that's not a universal choice. Then the next step is to split the words into characters that form the initial vocabulary. Really, it should be bytes, but I'm saying characters here just for simplicity and because in this case, they're the same thing. And now we're going to calculate the frequencies of all token pairs. So initially, these are just pairs of characters. We're going to calculate, or I guess, keep track of all of their frequencies. So we have TW, WE, and so on and so forth. And we can keep this like big table of all of the frequencies of token pairs. And once we have this, we're ready to start constructing our merge list. And we'll see that this merge list is actually what defines the tokenizer. So what we do is we find the most frequent pair of tokens, and then we're going to add it as a merge to the merge list, right? So the first merge is going to be the merge of L with E, and we're going to apply this merge to our training text. So now all instances where L and E occur next to each other now become a single token LE. Then we'll update our pair frequencies, and we can repeat this process again, where we find the most frequent pair, which is now T with LE. We'll add it to our merge list. We're going to apply that merge to our training text, update our pair frequencies, and kind of do this over and over again until we reach a predefined stopping point based on the size of the vocabulary. And this merge list actually defines the tokenizer because to tokenize new text at test time, the merge rules are applied in the same order that they were learned in training. So it's not actually the vocabulary that defines the tokenizer, which is probably a common misconception. It's the ordered list of merge rules from which you can actually infer the vocabulary. So for instance, if we're tokenizing this new word kettle, then you would apply the merge rules one by one until you're like out of applicable merge rules. And in this case, with this very simple merge list of 4 merges, we would tokenize kettle with a sequence of 4 tokens. Does anyone have any questions about BPE tokenizers, like how it works, how it's used? I'm going to pause here for 30 seconds. Yes, I think there's a question. Maybe you can just unmute yourself, or you can type it in the chat too, whatever you prefer.
Okay, I want to ask just a simple question.
Yes.
Is this related to how word embeddings work?
How word embeddings work?
Yeah,
In what sense?
like in the margin sense and in the way the training occurs.
So word embeddings, I think they're over like word. I don't remember if they're over words or tokens. Like back in the old day, like word to vec. Yeah, I'm not sure if they're over tokens or just white space delimited words. I don't know if that addresses your question, but yeah, models. The very first step is to embed all of the tokens into embeddings. That's like the very first projection matrix, and then in the end, you convert it back into a prediction over the vocabulary. Okay, I'm going to move on then. So now we can illustrate our problem setup. So given categories like English and Python, for instance, the idea is that different mixtures of these data sets will lead to different tokenizers, which are defined by different merge lists. So now that we've gone through how BPE works, you can actually check that these tokenizers are correct for this very simple data. So in this case, even though the tokenizers are trained on exactly the same text, because some text appears more than others, the ordered merge lists will look very different from each other. So for instance, to understand this better, if you have 2 copies of English text and 1 copy of the Python text, which is what's happening here, then the first merge we're going to learn is the merge of space with T. Whereas if the opposite is true, if you have twice as much Python text, then the first merge you learn is the open close parenthesis. So that's just based on how frequent these pairs are in the training data. What we want to do is reverse this process, namely given a merge list to solve for the mixture ratio that would have led to that merge list. And our key insight for how to do this is that the learned merge, our key insight for why this is possible is that the learned merge list is extremely sensitive to the mixture ratio of data distributions used in training. And we can actually notice this just from qualitative inspection, which is how we had the idea to start working on this project. So for instance, in the GPT-4o merge list, the first merge is the most common pair of characters, right? And in this case, it's the sequence of 2 spaces. And that might seem strange at first until you look at the next merge, which creates a single token from the sequence of 4 spaces. So this is actually a signature of substantial code in the training data because an indent is equivalent to 4 spaces by most coding standards. So what these first 2 merges is telling us is that the pair of spaces is the most common pair of characters in the training data for GPT-4o's tokenizer. And after we merge those 2 spaces, the most common pair of tokens is the sequence of 4 spaces. And so it's giving you a lot of signal for how much code there is in the training data. We also see double indents, and then we see this these strange characters. This is actually the byte level prefix for characters that are used in the Devanagari Unicode block. So this script is used for writing languages like Hindi, Nepali, Sanskrit, etc. And to make this a bit more concrete, so this character would be encoded as this sequence of bytes. So it requires 3 bytes to represent this character. And then each of these bytes, according to some mapping defined by OpenAI, would be represented with these characters. And so the idea is that all of the characters in this code block start with the same 2 bytes, which means that, so this appearing here as the 26th merge is giving you a sense of how common these languages are in the training data. We can keep going and looking around. This is the Cyrillic A, which is used in, for instance, Russian. This is actually different from the English A. So this A is represented as 2 bytes, which are then mapped to these characters, which is what you see here. And we also see semicolon new line. This is a very apparent example of code to me. I can't really imagine this pair appearing very frequently in any other corpus. So the key observation that's going to make our attack possible is that the Tth merge is the most common token pair in the training data after applying the T-1 merges, right? So the very first merge is the most common pair of characters in the training data. The second merge is the most common after applying the first, and the third is the most common after applying the first 2. And we're going to use this to construct our attack. So let's consider the first few merges from the merge list and say these are the counts of token pairs in English data and in Python data. So yeah, for instance, let's say space T occurs 2,000 times in English data and it occurs 13,000 times, 600 times in Python data, whereas the pair of spaces appears 13,000 times in Python data, and so on and so forth. That's kind of how you want to read this vector.
Alisa, sorry to interrupt you, but can you help me understand regarding the data part? Do you beforehand know that this belongs to English data and this belongs to the Python data, or is that an assumption that you're making right over here?
No, we don't do any, I'm just giving you, this is just qualitative observations.
Okay, got it.
We're not going to do any classification. We don't have any prior, purposes to sample. Yeah, you'll, I think, have that answered soon, hopefully. Thank you for the question. That's a really important clarification. So basically, so for instance, space T is appearing in both English data and Python data, right? It's not an English merge or a Python merge, but it has different frequencies in different data sets. So basically what we want is, what we know is that the mixture ratio defined by these coefficients, alpha, should be such that the weighted sum of these vectors has its maximum value at the index corresponding to the merge of 2 spaces, right? We know that this is true because the sequence of 2 spaces is the most common character pair in the training data. So for instance, imagine that in this case, there is 6 times as much English data as Python data. If that were true, then space T would be the most frequent merge, the most frequent pair. And we know that that's not true because it's actually double spaces that's the most frequent merge. So in this case, the first merge is telling us that English is no more than 6 times as frequent as Python data. So we're going to kind of keep doing this and building constraints on what the alphas can look like. So we do this again for the second merge. Now we're going to update our pair counts. And we know that the mixture ratio defined by these alpha coefficients is such that the index corresponding to the pair of double spaces is the largest. And we're going to do this again and again. In general, we know that at every time step, the mixture ratios should give a vector with a particular known index as the maximum value. So every merge is giving us more and more constraints on what values those coefficients can take. Does this kind of make sense to people in terms of like how, like what we're using to build the algorithm? Wow, thumbs up, thank you.
Can you repeat this one more time?
Yeah, for sure. So basically what's happening is that at every time step, you apply all of the previous merges, and then you look at the distribution of pair frequencies in every data set. And you know that we want like weights for every data set such that the weighted sum has a certain value as the largest one, right? So the weighted sum, it was going to be like a very large vector, and you always know which index needs to be the largest value because that's the true next merge.
Right, makes sense. Thanks.
Yeah, and that's kind of giving you constraints on what the alphas can look like. Yeah, so at risk of being too repetitive, because I think this is like a common question I get, we're not doing any like categorization of, oh, this merge is an English merge and so on and so forth, because lots of pairs of tokens will appear in lots of categories of data, but at different frequencies. So the idea is that that's giving you information about what the mixing ratio is for those categories. Okay. So we can, actually construct inequalities. So the count of the true next merge, which is the weighted sum of the counts in the different categories, has to be larger than the count for every other token pair, right? So for every P not equal to MT, we know that the count for MT is larger than the count for all the other Ps. And it turns out that we can actually use this to formulate a linear program. So to do this, we first add slack variables, one for every time step. So that's for merges that violate our constraints, and one for every pair for like pair counts that are surprising that violate our constraints. The reason we need to add slack variables is because it's not always going to be possible to satisfy all of the constraints because we generally don't have access to the exact same data that was used to train the tokenizer. So like, let's say the tokenizer is trained on some combination of English and Python data, but we have access to different English and Python data where the pair counts are going to be slightly different, maybe even out of distribution data, right? So we need to add these slack variables to account for like violations to the constraints essentially. Then the objective of the linear program is to minimize the sum of the slack variables subject to the constraints that we've built, where all of the constraints have this form. You might notice that, like naively, this linear program is like massive. It's because we have one of these inequalities for every pair of tokens, which scales like V squared, where V is the size of the vocabulary. And we're also like accumulating them for every merge, right? So this is like naively going to be, like empirically, it's tens of billions of constraints for the problems we look at. But don't worry, we solve it efficiently with some clever tricks, which you can read more about in the paper. I think this is a good point also to stop for any other questions about how the attack works. Okay, going to move on. Yeah, for the experiments in our first set of experiments, we evaluate our attack on tokenizers that we train on known mixtures of data categories. We're going to consider 3 types of tokenizers. So tokenizers trained on mixtures of natural languages from a set of 112 natural languages, tokenizers trained on mixtures of programming languages, and trained on mixtures of domains, which are all English domains, namely web, books, Wikipedia, code, and archive. And then for different values of n, we're going to sample n categories of data and also sample weights uniformly from the unit simplex. We're going to like sample some data for training the tokenizer and then sample other data for that's used in our attack. And we're going to consider the top 30,000 merges in the merge list because there's really diminishing returns from using more merges than that. And we're going to report the mean squared error of our attack, which is just like the average square difference between the prediction and the ground truth. So these are our results, and we're reporting the log base 10 MSE for better readability. So just to make these numbers more interpretable, this is like what random guessing looks like. Random guessing for n is equal to 5 would give you log MSE of negative 1.39. Yeah, looks like a random guess. And then for mixtures of languages, we achieve MSE that's 6 orders of magnitude better than random, right? So this is what our average, this is what our average guess is for languages. So this is what negative 7.3 log MSE looks like. So it's like really precise. If you look at the actual like numbers that make up these bars, the first 3 decimal digits are the same for a guess that achieves this kind of MSE. For code, we see that we're doing slightly worse than mixtures of languages. This shouldn't be surprising because we expect different, like natural languages like English versus Spanish, to be much more different from each other than different programming languages, which tend to share like a lot of syntactic features and English-like words. And finally, mixtures of English domains is the most challenging setting. This also like shouldn't be surprising. So here we achieve log MSE of negative 3.74, which like looks like this. So it's definitely doing something. It's telling you like information about the distribution of the domains, but it's not nearly as precise as our prediction for mixtures of languages. And then we also have results for different values of n. You can see that the MSE for languages and code is staying pretty steady, although notice that like random guessing gets better in some sense as like the MSE goes down for larger n. Yeah, okay. Does anyone have questions about the results or how to interpret them? On average, our attack achieves performance. Yeah, that's 2 to 6 orders of magnitude better than random. Okay, yeah. Why does random guessing get better? I want to say that's just how it works, but I don't know how to come. Like, I think on general, the differences will get smaller. Oh yeah, n is the number of categories. So if you have like 112 categories, the average difference between like a guess and the ground truth is going to get smaller and smaller with larger n. That's, I think, the right way to think about it. Oh yeah, John can also, you can write a more detailed answer in the chat if you want.
I think you did a good job.
Nice. Okay. So we also ran an experiment to see what happens when there are unaccounted for categories. So what if there are categories in the training data that we don't know of? Like these might be languages that we haven't accounted for or domains that we haven't accounted for. So we're specifically going to look at mixtures of 112 languages and omit between 1 and 50 languages when we're running the solver. So that just like, imagine we don't know up to 50 of the languages that are in the training data. The question we want to answer is whether we can still recover the distribution of the known subset of languages. So this is the relationship between the sum of probabilities of languages omitted, so the probability mass that we can't account for, and MSE, right? So you can see that it's like declining, the MSE is like getting gracefully worse as the probability mass increases. But it's actually surprisingly robust, I would say. So even if 1/10 of the probability mass is unaccounted for, like made up of languages that you don't know of, your MSE is still 10 to the negative 6, whereas random guessing is up here a little bit worse than 10 to the negative 4. Okay, so now that we've validated our attack in controlled settings, we're going to apply it to off-the-shelf tokenizers that are released with recent language models. We're going to run our attack over a total set of 116 categories. So this is because we split English, the English category, into 4 English domains, web, Wikipedia, archive, and books, so that we can give like more granular domain predictions. We're going to combine programming languages into one code domain because we don't really, I guess, care about the 37 programming languages, and we expect the distribution of programming languages to basically match the distribution on GitHub. So there's no need to do more granular prediction. And then we have 111 other natural languages. And we're going to study this following set of models. Any models that like are not in this list, but from the family, such as like GPT-3, you'll notice is missing, Llama 2 is missing. These are because they borrow the tokenizer of an earlier model. So for instance, Llama 2 reuses the tokenizer of Llama 1. And we're referring to these tokenizers by the models that they were released with. Yeah, do you have a question?
Yes, that is Claude 2, right? Because I'm not aware of Claude 3.
Yeah, this is actually it's actually Claude 1. That's a great point. So based on like a comment in the like code, it seems like Claude 2 and Claude 1 have the same tokenizer, and then Claude 3 introduces a new tokenizer that's not open. So we're not able to do inference for Claude 3. Yeah. Right. So, okay, over the next few slides, I'm going to talk about what is publicly known about these models and compare it with what we find. So let's first look at GPT-2. We know that GPT-2 used a filter for English. So they created an English-only pre-training corpus. And indeed, our prediction is that the training data is 99% English. For the domain breakdown, we infer that it's 84% web and 15% books. I would say the percentage of books is higher than what we would expect because it's trained on web text, which is supposedly just like web text. But the authors do actually report in the original GPT-2 paper some evidence of like book contamination in the training data. So this would, I guess, suggest that it's a little bit more widespread than previously thought, at least for the tokenizers training data. For GPT 3.5, we know that this is one of the first models that was trained on code. This was really exciting at the time because then work showed that pre-training on code grants models like strong reasoning capabilities because code teaches the model like similar step-by-step procedural skills that are used for reasoning. And indeed, we find that it's trained on a ton of code, 63% code. That's more code than natural language. GPT 4.0 was advertised as being super multilingual. The blog post says there's a significant improvement in non-English languages. Indeed, it's one of the most multilingual tokenizers that we study, and there's a very thick tail of non-English languages. So we find that like 68 languages make up at least 0.1% of the training data, which is like very non-trivial. In Llama's paper, it's written that the model covers 20 languages that specifically use either the Latin or Cyrillic script. So these are basically like Western languages like French, German, Russian, etc. would fall into this category. And indeed, we see that these 20 languages make up essentially all of the non-English data. So other like generally high resource languages like Chinese, Hindi, Arabic, all receive a prediction of 0.0% for Llama. It's like all built up into this 4% here. And for the domain prediction, we were also a little bit surprised because we infer that the training data is 23% English books, whereas the domain distribution is actually reported in the Llama paper, and what they say is like closer to 6%. So we're a little surprised. Our hypothesis is that books were upsampled for tokenizer training because it uses a much more standard vocabulary than the web. And this has been like observed by people before who were training tokenizers, and they report that if you train tokenizers on the web, you'll learn like really weird tokens, like long URLs will be learned as a single token because there's like tons of stuff on the web. So it makes sense that you might want to use a data source with a more standard vocabulary when you're training your tokenizer. Llama 3 is an interesting case because the tokenizer is actually borrowed from GPT 3.5's tokenizer with an extension of 28,000 additional merges. So we apply the attack to those new merges to essentially infer the data that was used for extending the tokenizer. So we find that it's primarily for like non-English use. They were adapting the tokenizer for multilingual use. You can see that from like the large proportion of non-English languages. And we actually reported this on the same day that the Llama 3 preprint came out. And they said exactly the same thing, which is that the Llama 3 tokenizer was trained this way to better support non-English languages. As you can see, the original 3.5 tokenizer has very little non-English language representation. So you're going to need to do something to the tokenizer if you want it to represent multilingual languages better. Then we have Mistral and Mistral Nemo. Mistral is natively fluent in English, French, Spanish, German, and Italian. Again, yeah, we're seeing like Llama, it has good representation of like Western languages, but not a whole lot of like other languages in the world. And in contrast, Mistral Nemo is said to be designed for global multilingual applications. And yeah, we see like a huge increase in non-English language representation. In general, if you look at these like trends within the same family of models, you're seeing like something clear, which is that newer generations of models are more multilingual, right? You're having more non-English data and less English data in correspondingly. GPT Neo X is a tokenizer that has been reused by many models, including OMO, Pythia, and the DataComp language models. We actually know that it's trained on the pile with vaguely certain components upsampled. I don't think we know which ones were upsampled. Our findings are pretty consistent with the pile, but suggests that books were again upsampled. So this might be for the same reason, which is that books is better training data or better tokenizer training data, or something like that. But the other numbers are pretty consistent with the statistics for the pile. And Claude, yeah, we don't know anything about Claude, including like the model itself. but we find that it's trained on more code than natural language. This tokenizer was reused for Claude 2. And we see that the Claude 1 tokenizer has very little non-English. So this is likely why a new tokenizer was trained for Claude 3, because they wanted Claude 3 to be more multilingual. And people have seen that it's much more multilingual. Gemma is primarily trained on English data from web documents, mathematics, and code. That's kind of consistent with what we see. And the tokenizer is huge, which is likely to support all of the non-English languages that we find in the training data. And for command R, it's also said to be very multilingual, serving over 100 languages natively. And we find this is like probably the most multilingual of the tokenizers that we study. I think, yeah, these are all of the predictions. So overall, we're like substantiating a lot of public knowledge about these models with new findings. Yeah, I actually think there is a way to uncover how much data was used to train the tokenizer. This is, sorry, a question in the chat where someone asked how to uncover how much data set, like how the size of the data set used for training. We don't actually do this in the paper, but we have an idea for how to do it, and I'm going to cover it like at the end of the talk. Okay, so I'll move on for now. Oh, we're here. Okay, so before I conclude, I have some more observations about tokenizers that we came upon during the project. So the first observation is that GPT-4o, for instance, has a lot of not safe for work Chinese tokens. So I'm just going to put my cursor on them here. So this is telling you something about how the training data was filtered, right? Like clearly this is in the training data, it passed the filter. This observation was also made by a Twitter user. And I'm sure it's not just Chinese, other languages as well. So it's giving you like a look of what's actually in the training data. The other observation we made in this project is that a lot of merge lists have these like triangular shaped clusters of merges. Oops. Yeah, so they're very obvious and it's extremely regular when you go deep enough into the merge list. So for Gemma, if you go like halfway through the merge list and then you keep scrolling down, it all looks like this. They're like triangular clusters of merges. So these actually occur due to tiebreaking, which is giving you a hint of the total amount of training data actually. So the more data you have, the less likely you are to have ties. So there's probably a way that we haven't really thought too much about, but there's probably a way to like figure out how much training data there is from how often ties are occurring. And then finally, we like saw that Gemma, Llama, and Mistral tokenizers use character-based BPE. So the units are actually characters. As you can see here, they're like characters that you recognize from different languages instead of bytes, which is what we see for Llama 3, for instance, and what we also saw for GPT-4o. This is a distinction that I don't hear about very often. So yeah, there's probably work to be done to understand why to choose one over the other. So these are both BPE tokenizers. The algorithm is the same. It's just that the base units can be either characters or bytes. Right, okay, so takeaways from our work. The ordered merge list of merge rules learned by BPE Tokenizer reflects the relative token frequencies in training. This allows us to construct a highly precise attack to recover the mixture ratio of different data categories. In general, these data categories can really be anything as long as you expect the word frequency distribution to look different. So we did, for instance, we recovered the distribution of natural languages, but we also recovered like the distribution of English domains. So different data sources that are all the same language. Then to take a step back, unlike model training, tokenizer training is a completely deterministic and transparent process. Yeah, so that gives us like a really cool window into model development, but it's very much overlooked for these kinds of like data inference problems. So hopefully our work is the first step in using tokenizers as an attack surface, but we believe there's still a wealth of information to be uncovered, and I gave a few examples of that on the previous slide. Like there's tons of information that's contained if you actually like take a look at it. That's all that I have. Thanks everyone for your time, and I'd love to take any questions. Okay, so Ahmad has a question. What would be the effect of NSFW words in Tokenizer for training a language model, even when the language model training has safeguards in place? If I understand correctly, so let's go back to that slide. Right, so the idea is that the if the tokenizer training data was filtered the same way as the language model's training data, then documents with these kinds of words are going to be in the pre-training data. You can then, like through alignment, implement safeguards, and that's what everyone does. It's impossible to curate a perfectly clean corpus for pre-training, and often you want the language model to like know about bad concepts and just not comment on them, which is why we have like pre-training data that's maybe more inclusive, but alignment data that enforces certain like normative beliefs about how language models should work. So you can still implement safeguards, and we don't really know how that's done, but this is at least telling you that this kind of text was like in the training data, at least for the tokenizer. And I suspect also the pre-training data, because I don't see why you would filter them differently. But that part I can't be sure of, yeah. And I should have explained this better also. This is, so that on the left side of the arrow, these are tokens in the vocabulary, and on the right side is just the English translation. That's how you want to read this figure, like, I guess, picture.
Alisa, I mean, thanks for the talk. Have a question. Does a greater proportion, you showed in the previous slide, if I'm not wrong, regarding the proportion of languages or the database that they come from. So does a higher proportion in a particular subject mean that the tokenizer or the model will perform much better in that particular subject, or does it give like better results as such? Because we see the command R and other gamma models having a larger proportion of multilingual data, and then
Yes, so
so
generally, yes. I have a slide on this. Wait, let me find it. Yeah, okay, so we implemented a baseline that's based on the tokenizer efficiency. This isn't exactly what you're asking, but it answers your question. So if you read this plot, what you see is like the larger the proportion of training data, like the larger the proportion a language occupies, the better the tokenizer will, like the more efficient the tokenizer will encode that language when you normalize it against like a base encoding efficiency for that language. So if you were to like only look at how efficiently it encodes a language, it won't be this well correlated, because some languages are just like easier or harder to encode based on like characteristics of the language itself. If you normalize it, then you get better correlation. So yeah, I think that is like what we would expect, which is why we have like why people are putting so many languages in the tokenizers training data. But it's, yeah, like if you were to implement a baseline based on this, which is again not what you're asking, it's a little bit better than random, but it's not nearly as good as our attack.
thanks.
Yeah. Another question, not sure if it is possible. Does your proposed attack also allow to uncover demographic or sensitive information? Yeah, I think this is going back to what I said earlier. We would, like in general, if you expect your different categories of data to have different like word frequency distributions, then it's possible to run our attack. Like there's a signal that our attack can use to give you a prediction. We haven't tried like really small, like we thought about like doing a category that's like New York Times or something like that to see if New York Times is in the training data. This would work if there are like distinctive features about New York Times that set it apart from even like other journals, right? Like other news sources. It's possible sometimes there are like artifacts of particular domains. So for instance, like Wikipedia, it's kind of easy to tell when there's Wikipedia data actually, because there's like a lot of like not only like entities, more formal language, like the topics are different, but there's also like headers that Wikipedia uses. So we saw, for instance, that like EX is merged really early if you train a tokenizer just on Wikipedia data, because every Wikipedia page has an external links header. And so then like the word external is like way more common in Wikipedia than like normal English data. And so then EX will be merged earlier. So like in general, if there's like artifacts like that, then it's possible for it to work for like very precise data sources. But it probably depends. But yeah, it would be a really cool application to have it work for like sensitive information. I'm going to go back to the takeaway slide. We have another question, which is, oops. Does data shuffle or data order also affect the results? No, it shouldn't. So, right, the first step of tokenizer training is to like split it into words, and then it's really just a bag of words that you're learning the tokenizer over. So the order of the training data has no effect on the tokenizer that's learned. Sorry, I'm just gonna go back to, so yeah, another question. I am curious to know the origin story of this research and where you would like to take this in the future. Yeah, so the origin story of this paper, I was looking at the Gemma merge list when Gemma first came out. So this was, I think, in March. And then basically I noticed a bunch of things that are very similar to what I'm showing on this slide. So there's a lot of like very interpretable signals of code in the Gemma merge list. So I remember seeing like open close parenthesis was merged really early in the merge list. So that means that like open close parenthesis is appearing a lot in the training data, and that's not very common in natural language, but it is very common in code. And then we basically teamed up and tried to like make this really mathematically rigorous and like derive the proportions in like a principled way. In terms of future work, I think like using tokenizers as an attack surface is like really promising and underexplored. And the other direction that I see is generally doing more abstract kinds of data inference for language models. So a lot of people are studying, for instance, like membership inference attacks. There's a lot of work on that. But it doesn't tell you like global information about the training data, obviously. And then there's also like kind of questions about how well it works and how well it's possible for membership inference attacks to work, especially now when language models are like really seeing most examples only once in the training data. So if there are ways to do like more abstract kinds of data inference for language models as well as tokenizers, that's a direction that I'm really excited about for the future. Thank you. Another question, what made you look at the merge list? When I was doing so myself, it felt even the original developers never had. It's true. So one thing that we noticed about merge lists is that they're like you could have, there's like a lot of redundant merges that we had to like get rid of because they were just like, people didn't seem to care about like the merge list that was actually released. Anyway, that's not relevant. What made me look at the merge list was because we have a tokenizer reading group, and I was up to present in the tokenizer reading group. The Gemma tokenizer had just come out. It was making a lot of waves because of how huge the tokenizer was. Other tokenizers have gotten like close to the size, but at the time, Gemma tokenizer was like really much larger than previous tokenizers. So a lot of people were talking about that, and then I kind of just did a deep dive into the Gemma tokenizer for that reading group presentation. And then during the presentation, I was like, whoa, wait a second. There's like a lot of stuff in here. But yeah, like tokenizers are really underappreciated. When we were reading like tech reports to like figure out what we do know and what we don't know about the training data for the model or the tokenizer, like lots of tech reports don't even have the word tokenizer in the tech report. It's just like no one really cares about the tokenizer. But actually these design decisions, like how you do pre-tokenization, whether your tokenizer is character-based or byte-based, a lot of these decisions matter a lot for the tokenizer that's eventually learned. It's just that, yeah, no one's really interested in it, I guess.
Also, Alisa, here, if you look at the slide over here, the amount of code representation for GPT 3.5 is greater than GPT 4.0.
Yeah.
Does that indicate that GPT 3.5's performance in code is better than GPT 4.0, or if my inference is wrong with regards to this slide? How should I infer that with regards to two models?
Yeah, it's definitely a part of the story. I mean, it's telling you how like efficiently you can expect a tokenizer to encode code, but there's a lot more to it in terms of performance, right? Like it's not just how well the tokenizer represents it, but it's also like whether you actually had training data for the model. Like in the worst case, you can imagine the tokenizer is trained on a ton of code, but then the model doesn't see any code. It's still not going to learn about code. But if it sees code, then with a better tokenizer, you'll be able to like represent it in a way that makes more sense, right? So for instance, like some of the early tokenizers don't merge spaces with each other. That's really bad if you want to represent code, because for an indent, you need 4 tokens. For 2 indents, you need 8 tokens. And that's like not a good way to represent code. So the tokenizer matters, but it's not everything. I expect the GPT 4.0 performance on code is much better than GPT 3.5, just because there were tons of other developments.
Yeah, that was my question exactly. No, because to add lower representation, I thought should I infer in such a way as such. But yeah, thanks a lot.
Yeah. Other questions? Can any information insights about the training data distribution also be uncovered from the trained weights of a language model. Yeah, I actually know someone who's working on this, and we might collaborate. So maybe it's possible. The question is to do the same process, but given weights to infer the data distribution. Yeah, I'm not really sure. It seems plausible.
If I can pitch in, I think the glitch token word kind of shows this exactly.
Oh, what does?
The glitch token word you
Oh,
cite,
really? Yeah.
we show
How
that
so?
the frequency of tokens in pre-training is correlated with some features of the weights, at least in Alma.
I'll have to take a closer look. I read that paper in great detail. It's a great paper. But I don't remember taking away that particular conclusion. Thanks. Stella asked, when training the GPT, one issue I ran into is that I basically have no understanding of how tiebreaking works. There are multiple different tokenizations of a single string of text. My current understanding is that this is why we were wrong about some of the properties of our tokenizer. If that's something you feel like we have a meaningful understanding of, it would be extremely valuable to try to explain that to people building tokenizers. Wait, I have to think about this one for a bit. Okay, so what I can say, oh, sorry, I don't want that. Give me 1 second. What I can say is that a merge list, when it's released, it's like a certain fixed ordering. So once you have the tokenizer, I don't think there should be multiple ways to tokenize text, right? Because you're going through the merges in a certain order. It's possible that when the tokenizer was being trained, ties were broken in a certain way. That may or may not be deterministic. But once you have the tokenizer, the encoding should be fixed. We actually have, we noticed that there is tie breaking going on for tokenizers trained. This is specifically tokenizers trained with the sentence piece library. I don't remember if this is what GPT Neo X used, if they use sentence piece. But so for sentence piece, if you look in the code, it actually tells you how ties should be broken. It's saying that ties should be broken from the smallest to the largest merge. So all of these triangular clusters of merges I see are representing our ties. I don't know how ties are broken in the Hugging Face library, but I don't remember seeing distinctive patterns that represent ties. Am I understanding your concern correctly? Is it about non-determinism at inference time, or weirdness about how the tokenizer ends up being learned? Conflicting merges. Okay. Oh, yeah, absolutely. Sorry, so Stella said the answer to my question is go read the merge list, not your list of tokens. Yeah, so this is why the merge list is what defines a tokenizer. So a single word can be tokenized in many different ways using tokens in the vocabulary. But if you follow the order of the merge list and you apply them one by one, then a word will always be encoded in the same way. Right, so for instance, pancakes, imagine that pan is a token, cakes is a token, but PA is a token and N cakes is a token. So there are, you can encode it as pancakes, you can encode it as P N cakes, but then if you apply the merges one by one, then you'll reach a certain tokenization, and it's probably going to be pancakes if your tokenizer is trained well. Yeah, the merge list contains a ton of information. So the merge list determines the vocabulary, but not the other way around. Yeah, for sure. So like n-cakes, if it's merged into a token, is probably not very frequent. So it's going to be very deep in your merge list. And you're going to reach pancakes first. This is probably a bad example for explaining this.
I can also
Yeah,
elaborate on this just for 1 second.
thank
Like
you.
there's to these, like there's certain, okay, if you're doing byte level BPE, there's certain languages that like live in a certain space in like the Unicode encoding. And what that means is like the prefix of that space is literally present in every single character in that language. So you might have a very small proportion of that language, but because that byte sequence appears in every single character, that pair will actually be super common. So like, yeah, like for example, I can't really see it, so I can't pronounce that name, but like those languages may not be that common in the training data, but because that particular merge always happens for every character, like the merge will actually still have a pretty high rank overall.
Yeah. Yes. Okay. Yeah. Another really interesting thing was that like different tokenizers use different pre-tokenization rules. This is also something that I like never, or like GPT-2 and GPT-Neo X, those papers talked about pre-tokenization, but basically more recent papers really don't say anything about pre-tokenization. So yeah, some tokenizers merge digits with each other and others don't. There's some speculation that if you don't merge digits with each other, then the model will like know numbers better because it like has a sense of like, yeah, like how big this number is, right? Based on how many like tens digits there, how many, yeah, digits there are. But other models make different decisions. So you might argue that for encoding a year, like 2020, you don't want that to be like 2020. You want it to be like the entity 2020 or something like that. I think what GPT-4o does is it only merges 3 numbers with each other. Like the largest token you can have of like numbers is 3 numbers, but not 4 numbers. So it's very odd. It might make sense. Like you might think of like numbers smaller than 1000 as being like more entity-like or something like that. I'm not really sure. I haven't seen that people add merges of digits manually. I have seen that people manually add merges of spaces. So that's what Gemma does. And I think, yeah, the GPT-3 tokenizer adds like merges of spaces to the end of GPT-2's tokenizer. But yeah, there are like manual merges that can be added. It's very easy to tell because it's very distinctive. So for instance, the Gemma tokenizer, the first like 1000 merges are merges of spaces with each other, merges of tabs with each other, merges of new lines with each other, and they don't correspond to like increasing a vocabulary ID. And it's like obviously manually inserted, so we just removed it because it wasn't learned by the BPE algorithm. GPT-3, no, it's really the same tokenizer, but they add like merges of spaces at the end. GPT-3 versus GPT-2. So the first like bazillion merges are exactly the same. There's just some extra manually added merges at the end for GPT-3. I guess Sanders providing information as well, which I don't know about. They reuse a tokenizer with multi-digit tokens, then turn on pre-tokenized digit splitting. Oh, yeah, that would make sense. You need to, wait, what? Pre-tokenized digit splitting? Okay, so then I guess those merges never get used, right? That's a little silly. Ah, I see. Yeah, unreachable merges. Yeah, I think a lot more care can be taken in how tokenizers are trained. Yeah, for sure. So, I mean, yeah, we will release our code very soon, but we had to do some like post-processing of merge lists to remove, for instance, like manual merges. We didn't remove like what we considered unreachable merges. We kind of just kept them in. Yeah, if it's unreachable, then hopefully the like Slack variables will take care of it. But yeah, there's also like redundant merges that we found, like merges that, yeah, I guess, yeah, those are unreachable merges. You can never get used. So we had to remove. It's, yeah, sorry, that's a little too much detail. Tokens that are in the tokenizer training set, but not the model training set. This is actually pretty related to glitch tokens. If Sander wants to answer this question, we didn't touch language models at all. So we didn't look at it ourselves.
Sure, I can touch on it. So yeah, they're all over the place. People do not use consistent data for their tokenizer training or model training. I think a lot of the weird spammy GPT-4 tokens, some of them at least, you ask what it means and it will hallucinate something completely different. And this is pervasive in pretty much every model. Yep. I have not managed to break Claude 3 because I have no idea how it works.
If you don't have any other question, we can conclude the session here, I guess.
Yeah,
Thank you so
final
much.
call for questions, I guess. Okay, yeah.
Thank you so much, Lisa, for your time. Really an insightful session.
Thanks for the invitation, and thank you everyone for your time joining the talk and listening in. If you have any questions or further comments, please feel free to contact us offline. We're really excited about this work, and we would love to keep talking about it more with everyone.
Thanks a lot, Alisa and Jonathan.
Bye.
Thanks, everyone.
Bye.
See you.
Bye.